I'm going to say this plainly. On March 11th, 2026, just before dawn breaks over the eastern horizon, humanity will witness the brief return of an interstellar visitor, Comet 3 I/ATLAS, the third confirmed object ever to enter our solar system from beyond it. No preface, no slow lead-in. This is the fact. And as someone who has spent decades studying the boundaries between what we know and what lies outside, I feel a familiar pulse of anticipation. This object has already passed perihelion in late February. It's racing away from the sun now, flaring faintly as sublimating ice breathes out into a coma we can barely register. And yet, despite its faintness, the window on March 11th will be our most favorable chance to catch it, if you have the right tools and if you know where to look. 1 hour before sunrise, low on the eastern horizon, near Sagittarius. Those three details define our opportunity. You cannot see it with the naked eye. Don't try. You'll see nothing. Its brightness is far below what the human eye can register. Even modest amateur telescopes will struggle. You'll need at least 8 inches of aperture, 10 or 12 inches would be better, and a clear, dark location far from intrusive city lights. Only then will you be able to glimpse that faint foreign whisper of light, its dust tail barely forming, its coma thin and quiet, its hyperbolic trajectory slicing past us with no intention of staying. This is not a bound member of our solar system. This is not a periodic comet that loops back every few centuries or millennia. The mathematics are unambiguous. The orbit is open, hyperbolic. The eccentricity is above 1. It came from the depths between stars and will leave forever after brushing past our sun. It is not gravitationally tethered to anything here. It is, in all the literal sense, a wanderer. What fascinates me isn't merely its trajectory, it's what its composition might reveal. Already, early instruments, particularly from ESA, have indicated traces of water ice, carbon compounds, and silicate dust. Familiar ingredients. They echo comets from our own planetary neighborhood. But familiarity does not imply sameness. What we need to look for are the subtle deviations, isotopic ratios, exotic compounds, structural anomalies formed under pressures or temperatures unlike those in our local environment. If some of those values diverge, even slightly, we will have direct evidence that planetary systems across our galaxy share material recipes, but mix them under different cosmic conditions. That is how you map the diversity of worlds without ever visiting them. Most people will never directly see 3 I/ATLAS. They'll rely on live streams from NASA, ESA, and university observatories instead, and that's perfectly reasonable. The comet is simply too faint, but faintness is not insignificance. In fact, subtle objects often speak the loudest in science. When we studied Oumuamua, we opened new debates about interstellar travel, about non-gravitational accelerations, about whether natural objects alone could explain its motion. With 3 I/ATLAS, speculation about artificial origin surfaced immediately, predictably. I addressed that head-on. This object behaves like a natural comet. It sublimates. It forms a coma. It responds to solar radiation in a manner consistent with cometary physics. So we can eliminate the artificial hypothesis early and decisively. But an object doesn't need to be artificial to be extraordinary. Think about the distance it has traveled. Millions, perhaps billions of years wandering the interstellar medium. Possibly ejected from a system closer to the galactic core, where gravitational chaos among infant planets or passing stars could have slingshotted it outward, a small icy time capsule forced from its birthplace by some violent celestial shove, then left to drift in the cold vacuum between suns until now. And for a brief moment in 2026, its path and ours intersect. That intersection is not trivial. It is an opportunity. The JUICE spacecraft, though not designed for comet observation, occupies a vantage point that instruments on Earth cannot replicate. It will gather its own data set, and by May 2026, when the downlink reaches us, we may find something unprecedented. A chemical signature, a structural marker, something that hints at the diversity of building blocks that form planets around distant stars. Every time we observe such an object, we're collecting comparative data, building a galactic census of materials. I'm not romanticizing this. This is the direct scientific importance of interstellar debris. It is the universe delivering samples to us, sparing us the energy cost of launching missions to other stars. We have no spacecraft capable of crossing interstellar distances within a human lifetime, yet fragments from other systems occasionally fall into our laps. If our telescopes are ready, if our analyses are sharp, if we know what questions to ask. And so, March 11th will not be a spectacle for the casual skywatcher, but a milestone for those of us who spend our lives studying the fabric of the cosmos. A foreign object will grace our sky just long enough for us to gather its secrets. That is why I'm speaking directly, without embellishment. This is a moment that matters, not because it glows brilliantly, but because it whispers truths from far beyond our sun. When I step outside that early morning, telescope aligned and calibrated, I will be looking at a messenger. Not a luminous one, not a dramatic one, but a real one, bearing chemical signatures from a world we will never see, from a star that may no longer even exist. The universe hides its stories in silence. 3I/ATLAS is one of those rare moments when silence briefly becomes visible. When I consider how best to observe 3I/ATLAS, I think first about constraints, because constraints define clarity. This comet is faint, unforgivingly faint. It does not reward casual effort or wishful thinking. If you want to see it directly, you must plan with precision. The moment arrives in the final hour before sunrise on March 11th, a narrow window during which the sky is still dark enough to reveal subtle structures, yet the comet has risen just high enough above the eastern horizon to escape atmospheric extinction. Even then, it hugs the horizon so closely that any obstruction, trees, buildings, even a modest ridge, will erase it from sight. That is the reality. Astronomy is not a spectacle. It is the discipline of respecting nature's limits. When I plan my own observation, I choose the darkest place accessible, far from urban glare, mountain foothills, desert plateaus, or isolated coastlines. Light pollution is the enemy of faint comets. A sky that appears dark to the human eye can still contain enough scattered light to overwhelm the tiny signal Atlas offers us. If the air carries moisture or particulates, contrast drops further. So the true observer must search for clarity in geography as well as in the sky, but equipment matters even more. This is not a comet that invites participation from all levels. An 8-inch telescope is the bare minimum, large enough to collect enough photons to lift the faint coma from the background. Larger instruments will do better, of course, but not because they make the comet bright, rather because they reduce noise. When an object is this dim, seeing it becomes an exercise in subtracting everything that is not the comet. Through a good telescope, once your eyes adapt, you may detect a faint smudge, an asymmetric haze, maybe the slightest elongation where dust lifts away from the nucleus. No vivid tail, no dramatic streak, just a quiet presence, a suggestion of motion frozen by the stillness of your view. Those who cannot observe directly will rely instead on live streams from NASA, ESA, or university observatories. That reliance is not a compromise. In fact, such streams often reveal more structural detail than individual amateurs can see because they integrate light over time, stacking exposures to extract a clearer profile. Technology democratizes access to the faint universe, even as it forces us to acknowledge that not all cosmic events are meant for the naked eye. While the world searches for the faint glow of the comet itself, I find myself more absorbed in its trajectory. A hyperbolic orbit is not simply unusual, it is diagnostic. It tells us that 3I/ATLAS arrived with too much energy to be confined by the sun's gravity well. Unlike bound comets that weave elliptical patterns, this object approaches once and departs forever. Its closest point to the sun has already occurred, and with it, the moment of peak heating, when sublimation peaked and the thin halo of gas and dust briefly widened. Now it is cooling, retreating, the coma shrinking, the tail fading like a breath in winter air. Hyperbolic geometry holds a certain poetic starkness. It reminds us that most of the universe does not orbit our sun, does not belong to our system, does not answer to our gravitational instructions. Objects like this are travelers. They enter our awareness briefly, then leave us behind. We only get one chance, and yet that one chance is enough if we prepare, because every interstellar comet carries a chemical fingerprint, one imprinted at the time of its formation. When our instruments detect water ice on a foreign comet, it is not trivial. It tells us that beyond our sun, in regions we may never visit, exists the same fundamental molecule that enabled life here. When we find carbon compounds, we take note. Carbon is not rare, but carbon chemistry is the language of planets and biogenic processes. When we detect silicate dust, we recognize the universal scaffolding of rocky worlds. But what truly matters are the ratios, the delicate balancing of isotopes forged in supernova and shaped by stellar radiation over time. That is why I'm fascinated by what JUICE may reveal in May 2026, after the data fully arrives from its vantage point. Unlike Earth-based telescopes, it observes from a quieter region, free of atmospheric interference and closer to the geometry of the comet's path. Instruments that were not originally intended for comet study may still capture meaningful information, spectral features, scattering profiles, subtle thermal signatures. When analyzing objects from outside our solar system, no dataset is trivial. Every bit of information carries the potential to unravel a question older than civilization. How ordinary or extraordinary is our cosmic neighborhood? I often hear the misconception that faint objects are synonymous with insignificance, that brightness determines worthiness, that the universe must impress us visually to hold scientific value. This is a misunderstanding born from our dependence on spectacle. 3I/ATLAS does not shine, it does not awe, it does not put on a show, but it carries something far more important, a portion of a planetary system that is not ours, a message written in frozen minerals, a story encoded in the way its orbit was carved by distant gravitational encounters. So on that morning in March, while many sleep, those who look will see almost nothing, a smudge, a whisper, a fragment. But the cosmos is not obligated to appear loud. Its truths often arrive quietly, disguised as faint streaks of dust and ice. And if we pay attention, if we listen through our instruments and analyses, we may learn what a distant star once formed, what forces shaped it, and what ancient violence sent it drifting into our path. 3I/ATLAS will not return, but the knowledge it offers will linger long after the comet fades into the silent dark between stars. When I think about how 3I/ATLAS was found in the first place, I'm reminded of how much our technological vigilance has evolved. The discovery occurred on October 1st, 2025 through ATLAS, the Asteroid Terrestrial Impact Last Alert System operating in Chile. ATLAS was never designed specifically to find interstellar comets. Its purpose is more terrestrial, detect threats to Earth. But in the process of watching for danger, it often catches wanderers. That's the beauty of continuous monitoring. The unexpected becomes visible. This comet slipped into our solar system silently, but Atlas noticed a motion inconsistent with bound objects. That slight deviation in trajectory became the first clue that we were looking at something from beyond our sun. Once the data was analyzed, the hyperbolic orbit became unmistakable. A normal comet repeats its path, returns after decades or centuries, but 3I/ATLAS carries too much kinetic energy to ever be held by the sun's gravity. Its path curves only once around our star before it escapes, accelerating outward into the void. And there is a psychological shift when you realize you're observing something that has not been influenced by the sun's life cycle or the planet's gravitational dance. It came from elsewhere. It belongs to elsewhere. We are merely the bystanders. What makes hyperbolic orbits so profound is that they let us trace possible origins. The inbound velocity, the angle of approach, the orientation of the plane, all of these variables suggest it may have been ejected long ago from a system closer to the galactic center. Near the core, stars are densely packed, their gravitational fields tangled, and chaotic. A young comet in such a system might easily be hurled outward by a close stellar encounter or by the violent rearrangement of giant planets in its home system. Once expelled, it would drift through the interstellar medium for eons, unbound, unclaimed, until fate aligned its trajectory with ours. To imagine that journey is to imagine cosmic exile, a small body thrown from its birthplace by forces far beyond comprehension, wandering among stars that never notice it passing, and now, after perhaps 1 billion years, it brushes past our sun briefly before continuing its escape. We are witnessing a piece of another world's debris, delivered to us by the randomness of celestial mechanics. But orbit alone does not tell the whole story. Composition matters even more. When a comet approaches a star, heat transforms it, ice sublimates, dust is expelled, gas glows faintly under solar radiation. These processes reveal what the comet is made of. From early observations, we already know that 3I/ATLAS contains water ice, carbon compounds, and silicate dust. These are familiar ingredients. They echo the same materials found in comets native to the Kuiper belt or the Oort cloud. But similarity is not proof of identical histories. What matters are the ratios, the microscopic details, the signatures of the star under which this comet was formed. If its water carries unusual isotopes, if the carbon has a different balance of heavier isotopes, then we may be looking at the fingerprint of a star with slightly different chemistry than our own sun. If its silicates display crystalline patterns that require specific thermal histories, we can infer the kind of environment in which it cooled. Every atom carries memory. Every compound is a clue. If we decode those clues carefully, we will know more about its birthplace than any telescope pointed across the galaxy could ever show us. This is why interstellar objects fascinate me. They are natural probes, pieces of distant systems that travel freely across the galaxy without requiring propulsion, energy, or navigation. Unlike spacecraft which we laboriously launch with fuel and intention, these comets move through the universe powered solely by gravitational interactions from their past. In a way, they are messages encoded in ice, dust, and radiation signatures, messages from worlds we may never see, a cosmic sample return mission without the cost. Some people still ask me whether 3I/ATLAS could be artificial despite the evidence. They remember the controversy surrounding Oumuamua, the debates about non-gravitational acceleration, the unusual shape inferred from its light curve, but this comet behaves like a natural comet. It releases gas, it forms a coma, its acceleration matches sublimation-driven physics. Its spectra show no indication of engineered materials or anomalous reflectivity. To cling to the artificial hypothesis would be to ignore straightforward data, yet I understand the instinct. Interstellar visitors feel rare, almost mythical. They invite speculation because they break the routine. We are accustomed to planets, moons, and comets bound to our sun. When something arrives from the outside, our imagination leaps. That is not irrational. Curiosity is what drives science forward, but evidence is what keeps us anchored. And the evidence here points solidly toward nature. But if nature alone sculpted 3I/ATLAS, then its significance is even greater. It means planetary systems across the galaxy likely share common chemical building blocks. It means water and carbon are not unique to our neighborhood. It means the emergence of organic chemistry may be widespread. And that is a more profound message than speculation about alien engineering. It suggests the universe is fertile, not necessarily with life, but with the ingredients that make life possible. This comet is a visitor from far away, but it is also a mirror. When we analyze it, we are comparing our solar system to another. We are asking whether our world is typical or rare, whether our composition is a cosmic standard or an exception. Every interstellar object that enters our domain gives us one more sample, one more data point, one more story to decode. And 3I/ATLAS, faint though it is, could be the most revealing interstellar messenger we have ever encountered. What interests me most about 3I/ATLAS now is not just what it is, but what it is becoming as it pulls away from the sun. Comets are dynamic objects. They react to heat, distance, and radiation, and in that reaction lies the information we need. When 3I/ATLAS passed perihelion in late February, solar energy surged into its nucleus. Ice that had been locked in darkness for millions of years began to sublimate. Gas escaped, dust lifted, a coma formed, faint, fragile, but real. These changes tell us about composition in ways no static measurement ever could. The sun becomes not just a light source, but an instrument coaxing the comet to reveal what lies inside. The coma of 3I/ATLAS is modest, almost shy. That in itself is a clue. If the nucleus contained large reservoirs of volatile material like carbon monoxide or methane, the outgassing would be more dramatic. The subdued activity suggests a structure dominated by water ice and silicate dust, with carbon compounds embedded but not explosively reactive. And this is where details matter. A comet's reaction to solar heating is a fingerprint of its internal layering and formation environment. How quickly it brightens or fades, how rapidly its dust disperses, how the coma expands. These features map directly to the thermal history of its birthplace. It's strange to think that by examining how a faint haze behaves under sunlight, we may learn about the temperature of a stellar nursery billions of years ago. But that's exactly what this is. Reverse engineering a distant sun's influence through the behavior of a fragment it created. The early ESA instruments have already detected water ice, carbon-rich compounds, and silicate grains. These results mirror elements we see in comets native to our own system, but the key lies in the subtleties. If isotopic ratios differ, even slightly, that difference becomes a marker of the star under which the material formed. Stars produce different proportions of isotopes depending on their mass, age, and fusion processes. A shift in deuterium to hydrogen ratio within 3I/ATLAS's water, for instance, could indicate its birthplace had a very different stellar temperature or accretion disk chemistry than our sun. Such small deviations would be profound. They would confirm that while planets and comets across the galaxy form from similar fundamental materials, the environments that shape them create unique signatures. Those signatures become the dialects of planetary systems, variations of the same cosmic language. This is why the data from JUICE matters so much. Although the spacecraft was built to explore Jupiter's icy moons, its instruments can still identify reflective patterns, dust populations, and spectral features invisible from Earth. From its vantage point, unburdened by atmospheric distortion, it may detect faint emissions that tell us about compounds that escape our ground-based telescopes. The data scheduled to arrive in May 2026 could shift our understanding of interstellar comets entirely. Imagine if JUICE reveals an exotic compound, a molecule rarely or never found in solar system comets, something formed only under extreme radiation near the galactic center. Or consider the opposite. Imagine if everything about 3I/ATLAS proves overwhelmingly familiar. That would suggest commonality across planetary systems. It would mean our building blocks are not special, but standard. And if the basic chemistry of the universe is uniform, the leap to universal potential for organic complexity becomes smaller. But beyond chemistry, there is the philosophical weight of these observations. Interstellar comets are not just icy travelers, they are archives. Their nuclei preserve the environment of their birth. They record the pressures, temperatures, and radiation histories of worlds long vanished. In the vacuum of interstellar space, these records remain unaltered for eons. And now, as 3I/ATLAS briefly interacts with the sun again, we have the rare chance to read those ancient inscriptions before they fade. This is why misconceptions about these objects frustrate me. People imagine comets as spectacular tales or dramatic sky events. They expect brightness, color, motion, but science often advances through the faintest signals, the quietest phenomena. A subtle spectrum can reveal more than a blazing tail. A tiny change in trajectory can rewrite theories. A dim smudge near the horizon can open a window into the chemistry of another world. 3I/ATLAS is exactly that, a dim smudge carrying truths from deep space. And when it leaves us, accelerating outward on its hyperbolic path, it will never return. It will not loop back. It will not pass the sun again. It will slip back into the interstellar medium, fade into the background of galactic dust, and continue its solitary journey. But the knowledge we gather now will remain. It will outlive the comet's visibility. It will refine models of star formation, improve our understanding of planetary chemistry, and mark one more point in our growing map of the Milky Way's material diversity. I often remind my students that the universe does not deliver meaning loudly. It whispers, and only those who listen carefully hear it. On March 11th, 2026, when the comet briefly rises in the dark before dawn, that whisper will appear in the form of a barely visible haze, one that carries the memory of a star we will never see. And to me, that whisper is enough. As 3I/ATLAS moves farther from the sun, its brightness will fade, its coma will contract, and eventually even our most powerful instruments will lose it to the dark. But the disappearance of an interstellar visitor is never the end of the story. In many ways, it is the beginning, because the data we have collected will continue to evolve. It will be analyzed, debated, recalibrated, and compared long after the comet itself has slipped into the unreachable distance. That is the nature of scientific encounters with transient phenomena. The object is temporary, but the insight is enduring. What interests me now is the origin question, the one that lingers whenever we trace an object's hyperbolic path back into the galaxy. The calculations place 3I/ATLAS's probable birthplace somewhere near the direction of the galactic center, a region dense with stars, gravitational turbulence, and young planetary systems forming in vast molecular clouds. In such an environment, comets are expected to be plentiful, remnants of planetary construction, fragments ejected by gravitational encounters, debris pushed outward by shifting orbits and stellar migrations. A young system can behave like a slingshot, flinging small bodies into interstellar space with velocities sufficient to escape forever. To imagine this comet's life is to imagine a world that may no longer exist. The star that once nurtured its ice might have changed, moved, or died. The planets that shaped its path may have collided or migrated. Everything that defined the comet's origin could be gone, leaving only this one survivor, an exile, carrying memories of a place erased by time. And now, after traveling for millions or billions of years, it has brushed past our sun, offering us a brief glimpse into that ancient environment. When I step back and reflect on 3I/ATLAS, I don't think of spectacle or brightness or public excitement. I think of the quiet privilege of witnessing something unbound, something that belongs to no star, no system, no cycle. A fragment of the galaxy passing us only once before returning to the silence between suns. In a universe this vast, encounters like this are rare, but rarity is what makes them powerful. If we listen closely, even a faint interstellar comet can teach us more about who we are, where we came from, and how many stories the galaxy still holds, waiting for the next traveler to wander into our sky and whisper its origin before vanishing again into the dark.